One of the fundamental ideas of abstract algebra is abstraction, of course. And when studying the various symmetries, relationships, and mappings of elements in groups, one natural question arises. If groups are generic interfaces for describing relationships and movements and mappings between elements, can we say anything about a group of these relationships themselves? Can these relationships be the elements in a group? Can we abstract one level further? This line of exploration gives rise to permutation groups, whose elements are those mappings, the very mappings which define other groups. In some sense, permutation groups act as fundamental building blocks for all other groups. So let's dive into defining and exploring these groups.
Before we talk about what a permutation group is, it would be wise to talk about what a permutation is. Formally, a permutation is a mapping from a set to itself. We can also view a permutation as a rearrangement of objects.
Let's say we have a permutation between elements in a set, some bijective mapping, and we want to easily write down the pre-image and image of this permutation, basically what happens to each element in the set. In comes array notation. Array notation is used to represent a particular permutation, where the upper row lists all the elements, and the corresponding entry in the bottom row is the image of that element upon permutation. Consider three elements of a set, represented here by three differently colored circles. What are all the ways we can bijectively, think permutation, map these three elements to themselves? We'll split into 6 different cases for the 6 possible ways that these 3 objects can be arranged, and let's number the elements to more easily represent them later in notation. In each case, we'll choose one arrangement for the image of the elements under a certain permutation. Removing the extraneous details, we're now left with what amounts to array notation for these permutations. These arrays show in the top row the object that we begin with, and in the bottom row the image of that object under permutation, which is some other object or the same object. This is one way of generating the symmetric group, in this case of 3 elements. Often, when we hear the word permutation, we associate it with a changing of positions. It might then be more helpful to track the mappings between positions of the objects instead of the mappings between objects themselves. So, let's make some placeholders for the objects, and again split into 6 cases. This time, we'll shuffle the objects around and track the positions, the starting and ending positions of each element. Unraveling this web of arrows yields the same group from before in a slightly different order. The difference here is that the numbers in the upper row represent some position that an object might start in, and the corresponding number in the bottom row represents the position where that object ends up upon some permutation. If this is slightly confusing, or if you're intrigued, I encourage you to rewind and rewatch these 2 animations to better understand the subtle but important difference between the 2. You might think that, I know permutations. That's the ways in which you can shuffle cards, or the ways in which you can seat children in a row of chairs, etc., etc. But these permutations act on sets, and sets don't have an ordering, at least not in that sense. The takeaway here is that permutations are useful for describing mappings and shufflings, but it's important that we define the set which is being mapped on. In the first animation, we were permuting the circles, and in the second, we were permuting the positions of those circles. Both of these cases did generate the symmetric group of 3 elements, but the interpretation of the numbers, the elements in the set, were slightly different.
Suppose we wanted to take the composition of the 2 permutations shown. We write this new permutation, sigma of gamma, as follows. Composition of permutations in array notation is carried out from right to left by going from top to bottom, then again from top to bottom. For example, sigma of 1 is 2 and gamma of 2 is 4. Therefore, gamma of sigma of 1 is 4. We'll move this column of the permutation gamma underneath the column that leads to it in sigma, and all other columns for reasons that you will see in a brief moment. Similarly, sigma of 2 is 4 and gamma of 4 is 2. Therefore, gamma of sigma of 2 is 2. Thus, we see under the composition, similarly, 3 maps to 1, 4 maps to 3, and 5 maps to 5. As we rearrange the columns previously, we can put the top row of sigma together with the bottom row of gamma to create the composition gamma of sigma in simplest form in array notation. Suppose we have the permutation alpha as shown. As 1 maps to 2 and 2 maps to 1, we can draw the permutation schematically as a circle, or cycle if you will, with an arrow from 1 to 2 and another arrow from 2 to 1. Then, as 3 maps to 4, 4 maps to 6, and 6 maps back to 3, we are able to draw another cycle similarly. And of course 5 maps to 5, so an arrow is drawn to itself. Although these diagrams are nice, they lack brevity, and as such we leave out the arrows and simply place the cycles into parentheses in what we call cycle notation.
Let's see how permutations in cycle notation compose. Here we have two permutations, represented as some combination of disjoint cycles in cycle notation, and we're going to compose them. Cycle notation is always taken right to left, so we'll join all the cycles together and observe where these cycles send each element. In this example, we have 5 elements. The element 1 is not affected by the rightmost cycle. The second cycle from the right maps 1 to 5, and the third cycle maps 5 to 4. So these two permutations, when composed in this order, map 1 to 4. Now where does 4 map to? Repeating the process yields that 4 maps to 1, completing our first cycle in the result. Let's watch how the rest of the process pans out. After we've tracked each element's mapping, the resulting cycle notation is complete.
Now that we've defined what a permutation is, as well as some ways to represent it, cycle and array notation, it's straightforward to define what a permutation group is. It's just permutations as the elements, equipped with function composition as the operation.
Consider the dihedral group of order 8 representing the symmetries of a square. Let's label each corner of the square with the Greek letter alpha through delta. The positions of these letters will move with the square. We'll label the location of each corner with the number 1 through 4. The position of these numbers will remain fixed. Consider a rotation by 90 degrees. Here, we see corner alpha in position 1 move to position 2. Corner beta in position 2 moves to position 3, and so on and so forth. We can then write the permutation in array notation for a rotation by 90 degrees in the dihedral group of order 8 as follows, representing a mapping between positions. We'll call this permutation rho. Let's repeat this once more, but with a horizontal reflection. Here, we see corners alpha and beta swap positions, and gamma and delta do the same. We can once again write this in array notation as a permutation, which we will represent as phi. Every element in the dihedral group of order 8 can be represented as a composition of rhos, the permutation representing a rotation by 90, and phis, the permutation representing a horizontal reflection, making it possible to represent the entirety of the dihedral group of order 8 as a permutation group. Consequently, this means the dihedral group of order 8 is a subgroup of the symmetric group of degree 4, which we will see shortly.
The symmetric group is perhaps the simplest permutation group we can define. It's just the set of all mappings from some set to itself. On screen now is the symmetric group for 4 elements, illustrated with cycle notation. Since there's absolutely no restrictions on what mappings can be in the elements of the symmetric group, it's therefore a parent group to all the other permutation groups. In other words, every other permutation group is a subgroup of the symmetric group.
We've actually already seen a symmetric group in action. Earlier, when we were defining array notation, we used all the permutations of 3 objects. That is the symmetric group of 3 elements. And here's that same group, just in a little bit more formal notation.
Say we have a Rubik's Cube, like the one on screen right now. For each of the 6 faces, we have a clockwise and a counterclockwise rotation that we can perform. Each of the clockwise rotations, all 6, will form the generating set of the group R3, the Rubik's Cube group.
Here are some useful definitions. Here are some useful theorems.
Let's look at Cayley's theorem. Essentially, this theorem says that every group is isomorphic to some group of permutations. So consider a group G, with elements G1, G2, etc., and a group operation star. Isolating an arbitrary element of the group, little g, let's define a function mapping from G to itself, where T sub G of x equals G star x. Given any little g in group G, we can similarly define a function based on little g inverse. Upon composition, which here I'll show in one direction, we can see that these 2 functions are inverses of each other. So these functions have well-defined inverses, and they map from G to itself, so they're bijective self-mappings, which is exactly a permutation. Now let's look at the set H, consisting of all such permutations that can be constructed from elements of G. This set satisfies associativity, because function composition is associative. It satisfies the existence of an identity element, namely T sub E, where E is the identity element of group G. It satisfies the existence of inverse elements, as shown before, and it satisfies closure. So H is, in fact, a group under composition, so we'll update our definition up top. Now let's define phi of little g to be equal to T sub G. Here we'll briefly show that phi is a homomorphism. Phi is surjective, since it is defined as a function, and it's injective because if phi of A equals phi of B, then A equals B. Therefore, phi is bijective, so it's an isomorphism. Thus group G is isomorphic to group H. Here we've taken a generic group G and constructed a group of permutations that is isomorphic, and thus we've proved the statement of Cayley's theorem.
Okay, this is our first outside of the textbook group property, yay! All it is that non-trivial symmetric groups are non-abelian. And by non-trivial, we just mean bigger than 2 elements. Alright, the proof of this is actually pretty straightforward. We're going to use induction. So the base case is that the symmetric group for 3 elements is not abelian. We just write that out. It's not abelian. Now for our induction step, we're going to assume that the symmetric group for k elements is not abelian, and we're going to prove that the symmetric group for k plus 1 elements is not abelian. On screen right now, I'm showing 2 possible values for a sub k and b sub k. To define a sub k plus 1, we note that there's only one place that the k plus 1th element can go, and that is directly to k plus 1. In other words, a sub k plus 1 is the only k plus 1 length permutation that can be formed from a sub k. Similarly, for b sub k plus 1, we define it the same way, just sticking k plus 1 onto the end. Since k plus 1 maps to k plus 1, we can write this as a piecewise function definition. So for each, it's just k plus 1 if x equals k plus 1. Otherwise, it's just a sub k or b sub k. Now we choose some x not equal to k plus 1 that doesn't commute according to a sub k and b sub k. According to the piecewise function definition from earlier, a sub k plus 1 of x is just a sub k of x, and similarly for b sub k plus 1. Therefore, a sub k plus 1 and b sub k plus 1 do not commute either, and so s sub k plus 1 is not abelian as well. For our next outside the textbook proof, we're going to prove that the symmetric group over an infinite set is uncountably infinite. First, let's define a couple things. We can just write out big X, the set, as x sub 1, x sub 2, x sub 3, all the way to infinity. Then we're going to define some phi inside the symmetric group of X, which obviously maps X to X. We note that phi can map x1 to any of the elements in X. In other words, we have the cardinality of X number of choices, and so on. Phi can map x2 to any element in big X, and so on for x3. In other words, for every element in X, phi can map that element to the magnitude of X choices. Therefore, the magnitude of the symmetric group for X, in other words, the number of phi transformations that we can choose, is equal to the cardinality of X to the power of itself. Since the cardinality of X has to be at least the Aleph null, this means that the symmetric group of X has to have cardinality greater than Aleph null. In other words, the symmetric group for X is uncountable, as desired.
One of the many applications of permutation groups is in cryptology, specifically encrypting messages. One simple method of doing this is the Caesar cipher, where letters are transposed to a shifted version of the alphabet. Let's shift the alphabet 3 to the left. Then, suppose we want to encrypt the word permutation. We can see how each of the letters are mapped as shown. We can represent the encryption and decryption of a letter using modular arithmetic and representing each letter as an integer 0 through 25. Then, we can use e sub n of x, representing the encryption of a letter x by shift n, to encrypt x and can decrypt it similarly. Here, the shift is 3, so n equals 3. As this is simply a permutation of objects, we can represent the Caesar shift by 3 as a permutation in array notation as follows.
Hopefully by now you've learned a little something about permutation groups and permutations and their relevance in abstract algebra and also to the wider world. There's some reflections on this topic and credits to 3 Blue 1 Brown's beautiful music in the description below.
This program was made possible by contributions to your UMTYMP station from viewers like you. Thank you.